All right, picture this. You're the lead engineer on a multi-million-dollar high-voltage project. You've done everything by the book, wrapped your communication lines in thick, premium shielding, grounded everything perfectly, and powered up the system. But instead of dead silence on the line, your scopes light up with massive, inexplicable, high-frequency noise. You haven't just failed to block the interference. Somehow, your incredibly expensive, shielded cable is actually acting like an antenna, pulling the noise right into your signal core. Welcome to The Explainer.
So let's dive straight into this engineering mystery. The truth is, the very geometry of your cable shield can completely transform it from a protective fortress into a parasitic liability. By the end of this explainer, I promise you're going to completely master the physical and mathematical intuition behind exactly why certain cable shields fail at high frequencies. We aren't just going to look at the symptoms here, we're going to break down the exact formulas governing this behavior, empowering your future hardware designs against these invisible electromagnetic threats.
Notice the sheer contrast between our options here. Over on the left, we've got a raw, unshielded twisted pair, which is incredibly common and honestly surprisingly robust if it's perfectly balanced. But look at that graph on the right. This curve represents transfer impedance, which is essentially a cable's vulnerability to noise plotted against frequency. Notice how that curve suddenly bends and just drops straight off a cliff as the frequency rises? The stakes here are absolute. If you choose the wrong cable geometry without understanding this curve, your noise immunity doesn't just degrade gently, it catastrophically fails exactly when your system's frequencies ramp up.
To understand how this actually happens, we need to look past the surface and dive straight inside the material itself. We've got to talk about the skin effect. Think of electricity kind of like a massive crowd of people rushing down a tunnel. At low speeds, or low frequencies, they spread out nice and evenly. But at a full sprint, at high frequencies, everyone gets pushed hard against the outer walls of the tunnel. Above roughly 1 MHz, this skin effect forces any alternating noise current strictly to the outer boundary of a cable's shield. Because the noise stays on the outside and the signal stays safely on the inside, a standard coaxial cable effectively behaves like a really expensive, double-shielded triaxial cable.
But here is the catch. How that outer shield is constructed changes absolutely everything. Let's look at this brilliant piece of engineering, the braided shield. Notice how the sets of conductors are interwoven, passing over and under one another in completely opposite directions? Let me give you a visual analogy for this. Imagine a braided shield as two overlapping highway lanes. If cars in one lane accidentally drift left and cars in the other lane drift right, those lateral movements perfectly cancel each other out. Because of this interwoven structure, the circular currents generated in the shield mathematically negate one another, leaving only a smooth longitudinal current flowing straight down the cable.
And this brilliantly illustrates the danger of our next geometry. Contrast that nice braid with this, the spiral shield. Now, manufacturers absolutely love these because they're super cheap to make and incredibly flexible. But look at that angled wrap. Sending high-frequency current down a spiral shield is exactly like forcing high-pressure water through a tightly coiled garden hose. Instead of flowing straight down, the current is violently forced to spin around and around the inner core, and as it spins, it stops acting like a protective shield and turns into a parasitic magnetic nightmare.
Let's move to the whiteboard and see how this builds a literal recipe for complete EMC failure. To find the exact point where a spiral shield stops protecting and starts destroying your signal, we have to mathematically break down the total shield current into two distinct directional vectors. Notice how the total current, which we'll call I, travels diagonally along that spiral path. Well, we can't really analyze the diagonal cleanly, so we have to split it up.
Okay, so the crucial point here is the math. Notice the pitch angle of the spiral, which we denote as phi. The total current, I, is our main vector. We decompose this total current into two specific formulas. Step 1, we have the longitudinal current. I sub L equals I times the cosine of phi. This is the safe current flowing straight down the axis. Step 2, the circular current, I sub C, equals I times the sine of phi. This second vector is our villain. This mathematical expression right here proves that the larger your pitch angle phi, the more destructive circular current you generate wrapping around your core. But what does that circular mathematical vector physically mean in the real world? Take a look at these spiraling lines of magnetic flux, denoted by the letter H. Because the circular current component, I sub C, wraps continuously around that dielectric core, it acts as a literal inductor coil. When current flows in a circle like that, it generates a highly concentrated magnetic field pointing directly down the longitudinal axis of your signal wire inside, meaning your shield is no longer blocking noise, it's magnetically inducing it straight into your protected data lines. Let's make this real with a quick walkthrough example problem. Imagine you're an audio engineer working in a studio using a highly flexible spiral shield cable. Suddenly, a nearby power supply injects a massive 1 amp common mode noise spike right onto your cable shield. You check the spec sheet and see the cable spiral has a pitch angle, phi, of 30 degrees. You're working with audio frequencies well under 100 kHz, but you need to know exactly how much of that noise is turning into an inductive magnetic field.
Let's pull out our formula for the destructive circular current. Step 1. We write the equation out. I sub C equals our total current, which is 1 amp, multiplied by the sine of our 30-degree pitch angle. Step 2. We evaluate the angle. As we know, the sine of 30 degrees is exactly 0.5. So we plug that in. Finally, step 3, we solve for the leakage. 1 amp times 0.5 leaves us with exactly 0.5 amps for I sub C.
0.5 amps. Just really think about that magnitude for a second. A full half amp of current is now circulating your internal signal core, exactly like a transformer coil. And this is entirely due to the sine of that pitch angle geometrically splitting the current. This mathematical reality perfectly explains why spiral shields fail so completely, becoming a huge inductive liability at higher frequencies.
And this brings us to the ultimate gotcha in hardware design. A lot of junior engineers just kind of assume all shields are created equal. They think a shield is just a piece of metal wrapped around a wire. But as we've just proven, the geometry dictates the physics. While braided shields mathematically cancel out those circular currents and hold off magnetic leakage up to roughly 10 MHz, spiral shields become a massive inductive liability above just 100 kHz. If you run a high-frequency digital signal through a spiral shielded cable, you are actively sabotaging your own system.
But wait, before you go betting your entire career on braided shields, let's examine their transfer impedance against frequency. Notice how the lines cleanly diverge around 1 MHz? That divergence is based entirely on the percentage of optical coverage the braid provides. Even braids have limits, guys. If you buy a cheap braided cable with 85 or 89% coverage, the physical holes between the weaves start aggressively leaking high-frequency noise. For the best shielding in rigorous environments, your braid absolutely must provide at least 95% coverage. Otherwise, it's essentially just a metal sieve.
All right, let's do a rapid-fire recap of the 3 atomic concepts you've mastered today. First, the skin effect is your best friend above 1 MHz, isolating noise safely onto the outer boundary of your shield. Second, woven braids perfectly cancel out lateral circular currents, keeping your signal dead clean up to 10 MHz. And third, spiral shields act as literal inductors. Governed by the rule I sub C equals I sine phi, they fail spectacularly at anything above 100 kHz. As the legendary Henry Ott once wrote, geometric ignorance is the root of most EMC failures. Well, now that you understand the math, you can actually master the noise. If you found this breakdown valuable, hit subscribe for more rigorous EMC and communication protocol survival guides. I want to leave you with this final thought. If a single mathematical angle can completely transform a protective shield into an active noise injector, what other hidden geometries are currently sabotaging the electronics sitting right on your desk? Something to think about. Catch you in the next explainer.